All right, welcome everyone. Today I want to cover some stuff from 4.4, which is economics. Lots of graphical stuff. I think it'll be a nice change of pace from 4.5, but then we'll go back to 4.5, and we'll probably do one or two examples from here as well. So I'm going to guess we'll do about 2/3 in 4.4, nothing too intense, and then maybe one or two more examples, some stuff from optimization. Bunch of homework help today and tomorrow. So 11 to noon and 2 to 3 for me, 4 to 5:30 Mackenzie, 6:30 to 8 Casey. The homework assignment that's posted is not due this Friday. All sorts of stuff are due next Friday. This assignment, particularly the problems from 4.5, can be challenging to set up. I mean, that's the hard part with these, and that's the whole point. They're word problems. So you need to translate from this abstract situation into something you can do math with. And that's not always easy. So be sure to ask for help. Give yourself time. Hopefully they're also fun and more interesting than just solving random problems. OK, so next week, as you're no doubt aware, is week 10. That's because this is week 9. So in Monday, we'll do a little bit of stuff from 4.6, probably not a ton. And then that evening, might be late, depends when I get to it, I'll post part A of the final. And that's the part that's like the midterm you do on your own. And that will be due Thursday morning at 11. So this part is much shorter than the midterm. So maybe an hour or two. So I'm really hoping that everybody can get it in then. The final, part B of the final, I'm going to maybe post part. Right, so part B of the final, that's sort of an extended foray into some of these optimization problems. And there are at least 4 different options. I might concoct a 5th. And I'll post those maybe today, maybe tomorrow, but soon. Those are going to be due part B. Again, you'll only do one of the 4 or 5 options unless you really don't have enough to do. And those you can do together, and you can get help on. And those are also pretty challenging. They're sort of like tiny little projects. But again, hopefully interesting and fun, a good capstone for the course, put together all of what you've learned. There'll be a lot of homework help week 10. I suspect it'll be mostly me and not the TAs, because it turns out it's week 10 for the TAs as well. Week 10s are usually a little easier for faculty. Well, so our workload gets often intense week 9, and then some kind of chills out week 10 when we just sort of watch you work, and then you hand in vast amounts of work to us, and you go off and have Thanksgiving, and we grade and we write about you for a very long time. Anyway, so there'll be a lot of homework help week 10, and it can be pretty flexible. So I'll post a few times, but let me know if there's some other times. And you'll definitely be wanting some help probably for this, and likely for the homework from there as well. So that's the rest of the term. Are there questions? Okay, you look so excited. All right, so the first thing I want to do is talk about the ability of dogs to do calculus, which I hope was entertaining. So this was the exact same problem that we solved last time, but instead of a person walking through the snow, it's a dog swimming through the water. So that's sort of optimization. Where should the person turn to walk through the snow most efficiently? This is where should Elvis turn to get the ball the most quickly. So OK, not a serious scientific study, but I found it very entertaining anyway. And it is sort of interesting that that dogs do that. I don't know. I'm not a dog person, so I'm usually quick to dismiss the cognitive abilities of dogs. If cats did that, I'd be like, well, of course cats can do that. But yeah, if dogs can do that, so that seems a little surprising. This spawned a series of follow-up papers. Do dogs know blank? Unfortunately, there were no follow. I'm unaware of any follow-up papers in this journal trying to do these tests on cats. Much more difficult experimental design. To do that. Were there any comments or questions or observations from this? That would be fun.
Running after the dog, right?
Well, just to measure, just to get the baseline, like I said, you can walk this fast in the snow and this fast on the sidewalk. So he had to do like, how fast can my dog swim? So and then how fast can he run? So that's how he was measuring those. That would have been fun to see, actually, chasing after his tiny little dog with stopwatch.
Influence the dog's path, because if the dog is followed.
I think this was just like straight on the beach and then straight in the water. Yeah.
Is there no one alley beach?
Yeah, I don't know. Lots of experimental design issues, definitely. A video would be great. Heather, you didn't find any videos of
No, the internet did have an obituary for the dog, though. It passed away at 12 years old.
Oh. How recent was that? Because I don't know. Okay.
I mean, also, maybe you can't trust it.
It's the internet, yeah.
I don't know.
Yep. That would be a really mean joke to play, though.
Yeah.
Posting a fake dog obituary. That somebody definitely needs a hobby, if that's what they're going to do. So yeah, a little bit of statistics, not the most powerful statistical analysis. But at least the dog's not always going in a straight line, and it doesn't always go in a right angle. So that seemed sort of interesting. Yeah, I forget what all the other papers were. Do dogs know optimization? Do dogs know related rates? Things like that. So yeah, anyway, hopefully this was entertaining. I always chuckle. There's always at least some little joke in here. I've read this a lot of times, but there's always some little joke I've forgotten. So I usually get a kick out of it. Any other thoughts on that paper? Hopefully that was a useful or entertaining 5 minutes of your life, however long you spent on it. It's about what it's worth. All right, so dogs may or may not actually know how to do calculus. Let me shut my computer down, because I didn't have a hard copy of this. All right, let's see, but back to people. Oh, and people and economics. OK, so sorry, my computer takes forever to actually. It usually takes longer to shut down than it does to start, which seems a little weird to me, but. All right. So we'll talk about some applications of derivatives to economics, particularly this idea of marginality and thinking on the margins. And this will be a little bit of a review, because we've talked about some of this before, and also a return to some of the graphical ways of thinking about the derivative that we've done before. So I think I want to say just enough to get you started on an example, and then have you start on that example, and then discover some things along the way. So let's see. So what do I want to say? Marginality. This is 4. OK, so what I'm about to sketch is a cost curve. So we're producing something. I didn't really commit to a specific example. I don't know what we should be producing. Last time we did students, thinking about how much it costs to educate students. Does anybody want some different example industry?
Cost to teach dogs calculus.
Cost to teach dogs calculus. All right, but dogs know calculus without, that would just be 0, because apparently dogs know calculus without any teaching at all. So let's see, who knows what this would be? These typically might have some sort of a shape like this. So this would be a cost curve. And this quantity is known as the fixed cost. It's how much you have to pay before you even get to make any of the things. So the machinery, or like building this room in which we learn calculus. And then as you produce more of the good, so what did we use before? We used chocolate. That was an example. We were making, when we did the product rule, that was candy. Chocolate. Or candy, yeah. Candy, pizza. And so anyway, whatever food we're producing, as you produce more of it, it costs more to produce it, because it takes things to produce things. Okay. But it's not always a straight line, and so this curve can sort of be interesting to look at. So let me think about C prime of Q. What would that does that tell us in economic terms?
Cost of producing it the next unit.
Yep, yeah, cost of the next unit. So cost, or I should say maybe additional of next unit. So just a blast from the past, difference quotients. It's been a while. But so, right, we can approximate a derivative by change in Q, change in C over change in Q. If we change Q by 1, that's what we're doing here. So this would just be the cost of the next unit, just like Clara said. OK, so economists have a special name for this, which some people must have encountered. Maybe we used in this class before. Marginal cost, yes, this is the marginal cost. And so I picture this like the margin is on the edge of your paper. And so sort of like, if you're here and you want to go one more, you're thinking like, what's the cost to make one more? So you're kind of at the margin or at the edge. And economists have a special symbol for this. Has anybody seen this in econ class? No, not yet. But it's similarly dreadful. So they like to use MC, which to any right-thinking person would mean M times C. But to an economist means marginal cost. So this is like one variable to Davis and people in his brother and sisterhood. Anyway. So I always find it, all kidding aside, although it is really fun and easy to make fun of economists, I always find it very disorienting, because I just really want this to be M times C. But it's not. Anyway, so we're not going to do tons of this notation. But this is really, you'll see this all the time. Like if you take economics classes, the board will be festooned with curves and straight lines and marginal costs and marginal profits and things like that. And it's exciting. You can actually get a lot of understanding from some simple understanding, but still it's understanding from some simple models. All right, so this is marginal cost. All right, so I think there's maybe one more thing to say. So here this cost curve has an inflection point. The concavity changes. Over here, where it's concave down, what does that mean from a sort of economics point of view?
For the first section, it will become cheaper as you produce more until you get to that point of concavity, and then the cost per unit will increase when you get to the second half.
Yes, except the cost per unit you're referring to as marginal cost.
Yes.
Right, which is different than cost per unit, which I'll say in a second. So right, so marginal cost is decreasing, and then marginal cost is increasing. So if marginal cost is decreasing, why might that ever happen? How could marginal cost decrease? It's economics. It's almost as easy to make up answers in economics as it is in evolution. Seriously, they just make up plausible sounding arguments all the time. It's a good thing this isn't being recorded. I could really get in trouble. Sorry. The next three things I just thought in my head and didn't say were even funnier, but I'm not going to say them. So anyway, why might marginal cost go down as you increase quantity? Surplus of quantity, demand, or just
You use the inputs in an efficient way, therefore the cost per unit.
yeah, there's some sort of efficiency increase, right? If marginal cost is going down, there's some sort of efficiency. And so it could be, what might an example be? I mean, so if, well, like to use the calculus example, once you pay me, there's very little additional cost. Like the difference between how much it would cost the school to teach a class of 1 student and a class of 30 students is very small. Because I don't get paid by the hour, and the TAs are only people that get paid by the hour. So this would be a very small thing. Some sort of efficiency. It could be, you need to buy chocolate to make your cookies or candy, whatever it is, and you get a better deal if you buy more of it, bulk discounts or something. What might happen that would make this turn around? So yeah.
You're increasing only one factor, which means that, like, you have, like, when you,
Yeah.
if you have more people coming to the class,
Yeah.
they don't fit, therefore your cost is.
Right, because you'll have to buy a new classroom. Yeah. Or buy a new calculus teacher or something like that. Yeah. Or maybe in order to increase production here, you need to buy a new oven for your cookies or something. So sometimes you get economies of scale, sometimes you might get diseconomies of scale. So anyway, so the concavity of the curve is sort of meaningful. And you might not know what this exact curve is, but you might have some sense of if it's concave down or concave up, and often that makes a really big difference in terms of how these economic arguments go. A lot of it depends just on the concavity of the curve. All right, so the last thing I think I want to say before I give you a sheet with a picture like this that you can draw lots of lines on is to think about cost per item. Maybe average, AVER, average cost per item. So when we average V, what in the world is V? That's actually a remnant from one of your problems for this week. So average cost per item is the cost of the items divided by the number of items. And this, in almost all circumstances, is always going to go up, or it certainly shouldn't go down. And we can draw that on a graph. That's a really bad Q. OK, so for a particular Q, I could say, all right, this is how much it costs to make Q chocolate chip cookies. And Q, that's the number of chocolate chip cookies, or this is the cost to get how many calculus students and so on. And so then the average is CQ over Q equals slope of that line. It would have been clever to draw A of Q closer to that. So anytime you have a ratio, you can think of it as some sort of a slope somehow in a graphical construction. Because a slope is rise over run. It's something divided by something else. So here, it's CQ over Q. I draw CQ, I draw Q, draw the line. So this must be, the slope of this is the average cost per student or per cookie or per whatever at this particular cube. And the main thing to note for now is that the average cost does not necessarily equal the marginal cost. So the average cost, was average cost larger or smaller than marginal cost here? So your average cost is a steep slope. The marginal cost is very little here. This is a place where you're getting really nice economies of scale. And so you might think, all right, if I'm here and I want to decide, gee, should I educate another person in calculus or should I make another cookie? It would be hard ever to imagine a way of a reasonable reason to answer those questions in the negative. Who could be against calculus or cookies? But anyway, should I increase production by 1? Well, you might say, well, gee, it costs me this amount per cookie. That's kind of a lot. But economists should at least know, and we all should know that we want to think on the margin. So it's not what's the average cost, but how much does it cost to make the next one. So they kind of sound the same and they have the same units, but they mean really different things. All right, so let's start into this example, which is sort of continuing this, and we'll see where this leads. All right, so let's see. So here's a cost curve. Marginal cost, which is just C prime. So here's a sketch of that. And so it's always positive. The cost is always increasing. But it's going up. Now it's going up less quickly. Almost hits 0, but not quite, and then goes steep again. So the marginal cost is going to look something like this, with a min where this line is the least steep. All right, so average cost is a little harder to see. Average cost is the slope of the line between my two fingers. So as I increase Q, the line between my two fingers is very steep, and then less steep, and then less steep, and then less steep still. I've sort of drawn them on here. And then right here, where this line just barely touches, or say this, the average cost when it becomes tangent to the curve. Like here, this line pierces the curve. It's not tangent to it, but here it's just barely tangent to it. And then as I go back along this curve, this line becomes steep again. So that would look something like this. And the main thing to note is that the quantity that minimizes the average cost is different than the quantity that minimizes the marginal cost. And so as I said, they're different concepts. They're both different ways of thinking about cost per item. And this trick of sort of seeing an average of something on a graph as this type of slope is a very useful thing outside of economics as well. And there are a couple of problems on the homework that have this sort of construction to them but aren't economic. OK. Questions on those?
How would you define that, like, algebraically or in the formula way?
Define what the average is, or the?
Yeah, well, you like define what the average is, but in terms of like showing the thought of that, like where that midpoint is.
I mean, so most of the a lot of the times this is just going to sort of be a graphical argument. I guess I've never thought of that algebraically, but I guess. What do I do over here? I guess if. So this is the average cost, and this is the marginal cost. And so this would be a condition at which the average cost is minimized, because here the slope of this line and the derivative of that are the same. I don't think we're ever going to use that formula, but I think that's a way to take this statement that I did with pictures and turn it into an algebraic statement. All right, so let's think about profit. Profit is how much money you get minus how much money you had to spend to get that money. So it'll be revenue minus cost. So I drew that there. So we want to think about maximizing profit. And let's think about that first on the graph and then in symbols. Kind of think about this a couple different ways. So what would you do? All right, so revenue minus cost. This is going to be your profit, that distance. So what could you do to make that bigger? Move it this way, yep. So you want to kind of wiggle around here until that line is about the largest it can be. I think that'll be maybe around there. So clearly, if you are up here, you want to make that bigger, you would produce less. If you'd move this way, if you're over here, say I want to make this difference bigger, I would move to the right. OK, so that's a graphical way of thinking of this. Let's think about this in terms of symbols. So profit, this is where pi comes in, just another absolute abomination of notation, because pi is related to the circumference of circles and has nothing to do with crass concerns of profit. But anyway, the economists see things differently, and they would write things like this. Doesn't it just turns your stomach a little bit? At least it does mine. So suppose, all right, so we want to maximize something. We take its derivative, set the derivative equal to 0, and solve for q. You've hopefully been saying that to yourself a bunch over the last week. So I'm going to take, again, I can barely write it, pi prime. Should be 0, because pi is a constant, like just same everywhere in the universe, but except for economists. So this is the derivative of c. This is the derivative of r. I'm just taking the derivative. So the usual thing, we set the derivative equal to 0, and we solve for q. This time we have q instead of x. So that means 0 equals r prime minus c prime, or c prime equals r prime. And if we had to turn this into something that economists like, we would not use calculus, but we would say MC is marginal cost. And we want to fathom a guess what this would be. Marginal revenue, yep. So again, any right-thinking person would immediately cancel the m's from this equation. But economists don't. This is how they write marginal cost equals marginal revenue. OK, so let's think about what this says. This says, all right, to maximize profit, we want to find the Q, production level, at which marginal cost and marginal revenue are the same. And that's actually what you were doing over here, only because you're a normal person, you weren't describing it in those terms. So if you're over here, and you might wonder yourself, gee, should I make more stuff? Should I increase Q by 1? And you're asking about, that's a question on the margins. So you would ask, OK, well, how much more revenue do I get if I up production by 1? That's your marginal revenue. How much more does it cost me? That's your marginal cost. And you're here and you say, gee, the marginal revenue is better than the marginal cost. The gain is better than the cost. I should do that. So being the rational profit maximizing person that you are, you would say, OK, yes, I will make more cookies. OK, so then you're over here. And you ask yourself the question again, gee, should I make another cookie? Again, it's very hard to come up with a situation in which the answer to that ever should be no. But you would say, OK, well, what's the additional revenue I get? All right, that's this. That's the marginal revenue. What's the additional cost? That's this. And again, the marginal revenue is larger than the marginal cost. Your gain is more than the cost. So of course, you should make that other cookie. OK, so now you're here. And now, again, you're saying, well, geez, I should probably even make more cookies because cookies are good. But you say, OK, well, what's the marginal revenue? It's this slope. What's the marginal cost? It's that slope. And you'll say, well, to a good approximation, gee, those slopes are the same. You know, I can't do any better than that. if I make a little bit more, it's going to cost exactly as much as it would make me, so I probably shouldn't do that. And surely, once you're over here, you would know, OK, should I make another cookie? If you're over here, your marginal cost is now pretty steep, so it's larger than your marginal revenue. Anyway, so this story, should I make another cookie, is just what this equation is telling you in economist language, or this would be in calculus language. And so the way to sort of eyeball the maximum is, well, you probably just sort of eyeballed the maximum, but it happens to be the point where the two slopes are equal. Does that make sense? Right. So let's see. There were a few more questions. So now we can imagine, all right, well, what if things changed? So suppose the picture here is now, suppose that the fixed costs increase. And the picture I had is that just means that it costs more to buy the machinery or to hire the faculty member. Like it's an older faculty member, older faculty cost more. So that would just move. That would just translate the entire curve up. So then the question is, what will that do to this optimal number of calculus students? We're not a for-profit institution, so that doesn't really apply. But or the optimal number of cookies in your cookie factory. Should you make more cookies or less cookies? OK, all sorts of answers. Or should you keep the cookies the same? You could do that too, I guess. Same. Yeah, you should keep them the same, because by shifting this curve, I guess there are a number of ways to see this. The way I think of it, because I tend to like algebra more than picture sometimes, is if you shift this curve up, you don't change the derivative. Right? So like my arm, so my arm has a derivative, a slope. Right? As I do this, I'm not changing the slope. All right. So right, you shift it up, you're just adding a constant to the function. It doesn't change the slope. And this tells us that it all depends on what the slope is. And if the slope doesn't change, then there's be no reason for the maximum to change. You're going to make less money, of course, because it costs you more now, because your machinery costs more. But just like these slopes are equal, those slopes are equal too. OK, so if you like this style of reasoning, you should take a lot of economics classes. Because like just, again, day after day with this stuff. And it's actually, I mean, it's sort of fun to make fun of, but it's also, it's a really nice way to think through, all right, if this rate goes up, what happens to this maximum? If this rate goes down, what happens to this other thing? So, I mean, it has its limitations, but it also has its beauty and use as well. And it's, fun to make fun of. All right, revenue per item increases. So this means you are now able to do this. OK, so now you are able to increase prices, so you have more revenue per item. And you somehow we'll assume it's still linear. And what would happen now? Should you make more or less or stay the same?
Are we looking at the first or the second part?
Let's look at the white, the white original cost curve, yeah. Same as we'll say more. So let's see. So by taking this line from here to here, we've made it steeper. So we've increased this. So we're going to have to increase that in order to keep this true. So another way to think of it is, OK, I'm here. This is my optimum, because I decided I'm not going to make any more cookies because my marginal revenue, my marginal costs are the same. I don't gain anything. But now, if we're in a new universe, where the revenue curve is steeper, now I should make more because the revenue curve is steeper than the cost curve. the marginal revenue would be bigger than the marginal cost, so I could get more profit if I move this way a little bit. So you should actually increase production, I don't know, maybe, like maybe to there or something. From like Q star to Q prime. And that sort of makes sense. Like if cookies are more valuable, it probably would do you well to make more of them. More valuable in the sense like you can get more money for them. You'll be willing to spend a little more money to make some cookies because you can get more money selling those cookies because cookies are worth more now. It's week 10 and people really need their cookies. They'll pay a little more. Week 2 or 3, you know, it's not such a big deal. All right, so I think, so this is economics. So, I don't know, let's see, is there a grand conclusion? I think one of the most important things that, and it's easy to overlook if you're kind of thinking too quickly, just in life and in general, is the importance of thinking on the margins. So rather than thinking about average cost, which is a more common way of thinking about things, asking what happens to your revenue and your cost if you do the next thing. And a simple example of that might be, and I always hesitate to bring this up, but it's now less politically charged. For years, there have been discussions about what size should COA be? How many students should we have? We've sort of settled that question. Not that everybody's happy about it, but we've sort of settled that question. Are any seniors around who were here for those big arguments? Probably not. OK, good. Because I think those might have been 4 or 5 years ago now, sort of receding in the rearview mirror. But one argument, OK, so at the time, the school's budget was not quite balanced. So we were like losing a little bit of money every year. And you might make the argument, so we're losing money every year. We have to pay money to educate students instead of us getting money in. And you, administrator, are thinking we should have more students. Isn't that a recipe for losing more money? And that's that's sort of a very logical sounding argument. But if we could add 2 students or 10 students without having to pay, well, I'd say that if the marginal revenue is better than the marginal cost, we should do that, even if the average cost is negative. So if we have a calculus class of 30, and you said, oh, well, let's just add 5 students, we get additional revenue, and there's almost no additional cost. Again, it's just the little hourly rate of the TAs. So anyway, sort of that was the argument. So a lot of people, including some faculty, quite a few faculty were saying, gee, we lose money on students, and the administration wants us to get more of them. Brilliant. Anyway, so we may or may not have, I mean, that doesn't settle the question, what size should the school be, because that's about a lot more than just marginal cost and marginal revenue. But a lot of people weren't thinking on the margins then. So anyway, thinking on the margins is a really good thing, and calculus maybe helps you do that, because it's all about marginal stuff. OK, so let's see, what do I want to do? I want to do a little bit more from 4.5. OK, so problems 1 and 2 on this sheet are not about optimization, but are just about proportionality. And so there's some quick proportionality exercises, partly because some of the questions from 4.5 are couched in terms of proportionality, and so you need to know how to decode that statement into an equation. And just thinking proportionally is maybe as valuable as thinking marginally. And then problem 3 is a little bit of an oblique but perhaps fun optimization problem. So we'll do that, just that sort of one example. So let's do 1 and 2, and we'll talk about those. And then we'll do 3, and we'll call it a day. So let me just say one thing about, or a few things, see if there are questions about these proportionality problems. And then we can focus on that last little alpaca thing. So stress is proportional to. So stress is proportional to. The is proportional to translates as equals k. And then caffeine consumption and inversely proportional to the square of this time thing. So when you have something that's proportional to 2 things at once, it's not a plus. They're all multiplied together. And when you say things are proportional, that means they vary in proportion to each other. So that means that if you double C, you would double S. You don't know, there's some constant that tells you how to convert from C to S, and it's unclear what units S would come with anyway. But they vary in proportion to each other. You double one, you double the other. Here, it's an inversely proportional thing. So if you doubled 1 over t squared, you would double this. All right, so if C is replaced by 2C, you double your caffeine intake. That's going to mean S is going to go to 2S, because you just put a 2 here. If t goes to half t, so that's what I was getting at with like from Thursday to Wednesday. So like you've got 2 days left, and now you have 1 day left. So your t got halved your t got halved. So what happened? Let's replace t with half t in here. And then I messed around to simplify the compound fraction. And the 4 ends up on top. So your stress level would actually go up by a factor of 4. So there are a lot of reasons why this model of stress is unrealistic. One of them is what would happen when you actually reach the end of the term. That means this would be 0, and your stress level would be infinite, which even though it may appear that way, I guarantee your stress level actually isn't infinite. Anyway, so this was probably not the most realistic example. This, however, is a realistic example. It is indeed the case that the power produced by a wind turbine is proportional to the cube of the wind. And that's actually a really important thing to know if you're thinking about wind turbines, because it means a little bit more wind means a lot more power, because it gets cubed. So if you are trying to decide between 2 locations, one of which is twice as windy as another, you might think, the twice as windy one should give me twice as enough power, right? Well, actually, the physics of it works out that it would give you 8 times as much power, because it gets cubed. If you're trying to decide between a location and one of which has 20% more wind power, so that means like v gets turned into 1.2 v, even that ends up being a big deal. 20% increase in wind speed turns into a 73% increase in power, because that 1.2 gets cubed. So you can get a lot of mileage and get a lot of thinking done just by knowing what's proportional to what. And is it a square, is it a cube, is it inverse, and so on. OK, so the last problem is about alpacas and T-shirts. Spend a few minutes reading that, and it's a little hard to get started, but the usual place to start is to write down what you know and then see if you end up knowing enough to get started. So anyway, give that a try, mull it over for 5 or 10 minutes, and we'll talk through it. So this problem, at least I think, which I know I didn't think up, but I couldn't track down where I came up with it. The alpaca connection, that was mine, but the other part of it was not mine. So the picture is if you price you've got 45 T-shirts, and you think, oh, I'll sell them for $10. I know I'll sell them all, so that would give me $450. But then somehow you know or think or guess that for every $1 you increase the price, you'll sell 3 less shirts. So for example, if you priced them at $11, then you would sell 42. And you'll think, well, that's a bummer. I'm selling less T-shirts, and I'm wasting 3 shirts. But if your goal is solely to maximize profits, which you then reinvest in your alpaca business, you should do that and just burn the other shirt. Or feed them the alpacas. Maybe alpacas will eat them. I don't know. So you would get more by selling less because your price is higher. So then, so then even more, even more, even more. Eventually, that story is going to turn around, presumably because you're going to be selling so few of them. So that's a way to think. Right? These min-max problems, there's usually some sort of a trade-off. Well, gee, on the one hand, I should do this. But on the other hand, I shouldn't do too much of that, because then that'll be bad. Right? So maybe just doing this little calculation sort of helps you frame it in those terms. OK, so what do we know? At $10 a shirt, you sell 45 shirts. I also should have written out the sentence, every additional $1 you charge, you sell 3 less shirts. So all right, so revenue, that's going to be the cost of the shirt times the number of shirts sold. And then I'm going to need a variable someplace. And I thought, well, I'm going to have X be how much more than $10 the cost is. And that's not a great sentence, but anyway. So then the number of shirts sold is 45 minus 3 times the additional dollars. And the cost is 10 times X, because X is the additional dollars. So this is going to be my revenue.
Wait, 10 times or 10 plus?
10 plus, thanks, yes. Yep. 10 times that would be exciting.
Yeah.
So, and you can already see here, like, again, sometimes, right, there's always this trade-off. Well, on the one hand, you should do this, but on the other hand, you should do that. And sometimes you can sort of see that in the formula itself, because this increases with X, and this decreases with X. So you've got this term getting bigger and this term getting smaller, and so there's got to be some balance where the increase of one and the decrease of the other sort of equal out. All right, so now we know we have to take the derivative, set the derivative equal to 0, and solve for X. And you could use the product rule, or you could FOIL, and then not use the product rule. What are people in the mood?
Product rule is better.
Product rule? OK, I FOILed, but this will be exciting. All right, so R prime, let's see what we get. Take the derivative of this one, leave that one alone. Derivative of X is 1. The simplicity of that does recommend that there's the product rule. Then leave 10 plus X alone. Take the derivative of 45 minus 3X, that's minus 3. So let's see here. So R prime is 45 minus 30 minus 3x minus 3x. Yeah. So R prime is minus 6x plus 15. Yep. Which, not coincidentally, is just what you'll get if you FOIL and then take the derivative. Math being nice that way. All right, so let's set R prime equals 0. Let's solve for X. All right, so I've got 0 is minus 6x plus 15. 6x equals 15. So X equals 15 over 6, which is 12 and 2.5.
Yep.
So you should sell the t-shirts at $12.50. You won't sell all of them, but you can either feed them to the alpacas or burn them in a fire, which will heat the alpacas. Or recycle them or give them away or something. But you wouldn't want to tell anybody you're giving them away, because then any rational person isn't going to pay $12.50 for something you're about to give away. Economics. All right. So this is an optimization problem, but it's sort of in a revenue maximizing context, so I thought it went well with today. On Monday, we will do a few related rates problems, maybe another optimization problem. Again, just using derivatives in different ways. And then the term will begin to wind down, at least for me, if not for you.